So why is electron microscope superior compared to the optical microscope? Just now we have been saying that in the field of biology or chemistry or physics, we are favoring electron microscope when we are taking pictures of very tiny objects, which includes like a row of atoms maybe, or a very small crystal structure that we want to observe its lattice inside. Or you can talk about some microorganisms or even viruses that you want to study their structure, their internal structure. Electron microscope is very much favored compared to optical microscope. And so this is the video which will explain why is it advantageous for electron microscope. So for optical microscope, we are operating using visible light. So visible light spans through a wavelength of 400 nanometer to 700 nanometer, somewhere around there. So we can say that usually we use a wavelength which is around hundreds of nanometer. That's the way to say it. So this is according to the electromagnetic spectrum. You have your radio wave, microwave, infrared, visible light, ultraviolet, X-ray, gamma ray. For visible light, it spans around 400 to 700 around there nanometer. Okay, but if you talk about electron microscope, you have to remember that electron also undergo diffraction because it behaves like a wave. This is according to the de Broglie's hypothesis, which has been proven by Davison's Gilmer experiment. So we are going to operate electron microscope using moving electrons. So we know that when the electrons are moving, they have a momentum, and that momentum can be related to its wavelength. So usually when we are using an electron microscope, we are connecting the accelerating anode. You can refer to what is accelerating anode in the previous video. You can usually apply a voltage of around 15 kilovolt, around 15,000 volt. You're going to apply it to the accelerating anode in order to speed up the electron before it passes through the object. So if you apply an accelerating voltage of about 50 kilovolt, what kind of wavelength will you get can be determined using this equation over here. Okay, this equation is derived in the Davison-Gilmer's experiment video, in which we try to relate between the accelerating voltage and the wavelength of the electron itself. Okay, to understand how this equation comes into place, maybe you should refer to that video when we discuss the Davison-Gilmer's experiment. But for here, we are going to substitute the Planck constant, which is a constant 6.63 times 10 to the power negative 34. This is your mass of electron, your elementary charge, and also the accelerating voltage, which is usually around 15 kilovolt. Okay, you substitute these values inside and you get a wavelength which is on the order of times 10 to the power negative 12. So already from here you can see a significant difference in the wavelength that you're operating with when you're using optical microscope or when you're using electron microscope. For optical microscope, we are operating on the range of nanometer. Okay, but for electron microscope, we are operating on the range of picometer. In fact, it's not correct to say nanometer because it's 100 nanometer. It's very near micrometer already. For light, you are operating near micrometer range, but for electron microscope, we are operating around picometer range, which is very big in terms of their difference. The difference is about times 10 to the power negative times 5 order of magnitude difference. Means by about a tenth of a million kind of difference. How should I say it? 5 order of magnitude. 5 order of magnitude means it differs by 10 to the power of 5. Okay, if you take 10 to the power of negative 7 multiply by 10 to the power of 5, you get 10 to the power negative 12. So it means they differ by 5 orders. Okay, they differ by 5 orders, which is a very large difference. That's the main idea that I try to say here. Okay, so you can see that optical microscope uses a much larger wavelength, whereas electron microscope uses a much smaller wavelength. So we know that this wavelength over here will affect the diffraction pattern that we see, because we know that d sine theta is equal to m lambda. So if you are using a larger wavelength and you fix your m, okay, you study m is equal to 1, let's say the first order only you study. If you use a larger wavelength, what will happen is you get a larger theta. Okay, your d is fixed. Okay, d is fixed. It's the size of it's the distance between the atoms of your image, of your object basically. Okay, don't worry too much, but d is fixed. Your lambda is different for optical and electron microscope. D is fixed, m is fixed. So if you have a larger wavelength, you have a larger theta. Okay, so you should expect that for optical microscope, you have a larger theta, means by diffraction spread out wider. Your diffraction spread out wider, you have a broader diffraction pattern. But for electron microscope, because your lambda is smaller, your theta will be smaller. Again, your m is fixed, your d is fixed, so smaller wavelength means smaller theta. Smaller theta means by your diffraction pattern only spread out by a little only. So you get a very more localized, more narrower diffraction pattern. So you should expect the light will spread out quite widely for light, but for electron, you spread out very little. The kind of diffraction pattern is very little. Okay. This equation again is out of syllabus for chapter 8. I'm only explaining it to you using this equation because I want you to see the rough idea of how one thing relates to another. Again, all these are just concept. It's good for your understanding, but it's not required for you to answer. You are not required to use this particular equation to answer chapter 8 questions. Okay, it's just for you to get a sense of how everything relates together. So the idea is larger wavelength causes larger angle. So larger angle means you are spread out wider. For electron microscope, it's smaller wavelength. Smaller wavelength means smaller theta. So your diffraction pattern is more localized, it's narrow. Okay, so if you have a broader diffraction pattern, what happens is you have a poorer resolution, because let's say the left eye of the cat spread out by that much, the right eye of the cat spread out by that much. So in that case, they spread out so much that they overlap each other significantly. You're not able to differentiate between the two eyes of the cat. Okay, of course, cat you're able to differentiate. I'm just saying an example. Okay, but for electron microscope, right, because your light spread out only by a little, your light spread out only by, not like your electron beam spread out by a little, your electron beam spread out by a little, so they are not overlapping with each other significantly. So if they are not overlapping with each other significantly, you are able to differentiate them clearly as two details separately. So in that case, you can say that the image produced by electron microscope will have a better resolution. Okay, so the idea is larger wavelength for light causes larger theta, means by broader diffraction pattern, poorer resolution. For electron microscope, smaller wavelength, therefore you have a smaller theta or narrower diffraction pattern, so you have a better resolution. Okay, over here I attach an equation which is again not required for you to use, just attach here for you to get a sense of idea how everything relates to each other. So you can see that if you have a smaller wavelength, okay, if you have a smaller wavelength, this is the diameter of the lens aperture, means that the opening of the lens is how big. But by using a smaller wavelength, you get a smaller theta. Okay, means by your resolution, it's you have a better resolution because you have a smaller angle. Okay, but if you are using a larger wavelength, which is this case, a larger wavelength, you get a larger theta. So larger theta means by you are more spread out, so you have a poorer resolution. So this is the equation that we usually use to be able to see whether we are able to resolve something or not. Whether two things are able to resolve to be seen as two clear details, or they merge as one big blob. Okay, this is the equation, but again, it's not required to be used in your exam. It's just, I just put it here for you to get a rough sense of things. Okay, so to put it into, let's do a short conclusion of everything. The idea is electron microscope is much superior compared to optical microscope because electron microscope operates on a smaller, shorter wavelength, therefore it has a better resolution.